Alright, so here we are going to talk about the MEMS devices which are based on the capacitance change, and we'll talk about the parasitics. In that we'll talk about the capacitive feed through, and we'll also talk about the equivalent electrical circuit of the of your mechanical transducer. And then for a mechanical device, for example a resonant transducer, we have the quality factor. We'll talk about that, and then we have to convert the mechanical motion into an electrical signal. So for that we need a readout circuit, so we'll also discuss that. So so to begin with, let us take a simple example of what is mechanical transducer and how it makes a transduction via capacitance change. So for example, this is simple beam, and let us say it is clamped at both the ends right over here, and beneath this beam we have an electrode which we are going to use to drive this beam into vibration. So before we can drive this beam into vibration, what we are going to understand, for example, let's say we apply a DC voltage to this beam over here, and let's say we apply this DC voltage. This is a resistor R, and we call it as a VP, which is used to polarize this capacitor to this beam with respect to ground. All right, so and this is at DC ground. All right, and then what we are going to do is, when this is put into action, this voltage is applied, there is a creation of an electrical field across this capacitor. So now there is this capacitor over here between, because this forms a parallel plate. Alright, so now we are going to apply an AC voltage to this bottom electrode at certain frequency. So what is going to happen here is we have this beam, and then we have this electrode. We apply AC voltage to this electrode, and the DC voltage VP is applied to the beam, which is clamped at both the ends. So there is a creation of an electrostatic force, as we have seen previously, Fe, and we see that that is proportional to epsilon A over D minus X whole square VAC into VP. So this Fe is at the drive frequency. We've seen that in the previous class. All right, so with that, so where is this where is the output? So we have an input of this circuit over here. We say that this is an input of this, this is a mechanical circuit now, and where is an output? Output we can take from this end. So what we do, that we have the same body of this beam over here, and from the body of beam we put a capacitor here to just to block this DC voltage over here. And then here we have the motional current, or say the current due to the motion of this vibrating element. Okay, because when there it vibrates, there is a change in capacitance, uh, and the gradient of which dc dx is given by epsilon a d minus x whole square. We've seen that previously. So that is a capacitance gradient, and then this the current gets generated, which is uh, motional current. We'll see that what is motion current. We've seen that that is called IM, motion current, and that gets available over here. So we'll derive an expression of motion current as well, but before that let us see what is now feed through over here, or what is this motion current. First let us take a look at that. So what we have to understand here is there is this parallel plate capacitor over here. So when we are sensing the output current, which is available here, there is also another component of current that comes from input to output. So here is an input and here is an output of this mechanical transducer, and so there is another component of current that is coming from input to output over here. So this IT is basically contains two components. One is IF and one is IM. So IM is called as the current due to motion, mechanical motion of this transducer, and IF is component of a current which is called as feed through current. So it's due to the inherent capacitance that is formed between this beam and the electrode beneath. So there is because of this voltage over here, we have this current through this capacitance that is going to be added with the current in the motion. So the total current IT is summation of these two components. So how to derive an expression of IM and IF? So for example, we can write the current, which is the total current. Okay, so current is basically a change of charge, uh, derivative of dq dt, where q is the charge, and then we can write this as dcv over dt. So q is c into v, which is capacitance into voltage. Then we can uh, write this expression as capacitance. So there are two variables, so we can write as a c, derivative of this voltage, and plus v dc dt right here. So there is a capacitance variation here because of the displacement. So we have this component over, and due to this feed through direct, we have our input voltage, and then there is a capacitance, and this current, there is a signal that goes like this. So that is another. So this is the component of feed through, and this is the component of motion. We can further write it as I of I is equal to CO, which is this capacitance, which is inherent capacitance between these two plates. And what is the voltage? That is Vi of t. So this voltage over here, that is Vi of t. So it may be a Vm sine omega t, that is an applied AC sine wave uh, with respect to time, plus we can write this Vp, that is because now we have a voltage over here, so we can write the total voltage is V is like Vi plus Vp. So we can write here is Vi plus Vp. So generally Vp is very greater than Vi, because this is the small signal AC voltage and this voltage is DC voltage. So we can then just simply write, we can neglect the AC magnitude of AC voltage and we'll just write Vp. Okay, and that is capacitance, change in capacitance with respect to time, dc dt. Okay, so that's the total current that we can write, we can get of this transducer right over here. So it contains two components. One is due to feed through, which is inherent in the device, and one is the motion current due to the motion. That is how it can be written. So furthermore, what we can write here is this current. So this is IF and this is IM due to motion. So we can write motion current as Vp, and dc dt, which is the derivative with respect to change in capacitance with respect to time, can be written as dc dx into dx dt. So it's essentially same, because dx gets cancelled over here, and which can further be approximated as eta times dx dt. So eta takes the form as Vp into dc dx, which can be written as Vp into epsilon a by d minus x whole square, because dc dx is what we have written here. So that is how it goes. So furthermore, the total current can be written as I of t is equal to CO, which is this static capacitance, and derivative of input voltage Vi of t divided by dt plus eta dx dt, and we can furthermore write it as we have this current, this feed through current can be written as admittance into the voltage, which is Vm sine omega t, and admittance can be written as dx dt. So it can be written as admittance is of the capacitance is j omega co Vm sine omega t plus eta into dx dt. So that is how it goes. So this structure is called as a one port structure, one port transducer. One port is in the sense that we just apply voltage to this electrode over here, and we are actuating this transducer across this capacitance gap. So this is a gap over here indicated by D, and we are sensing the output signal across this capacitive gap itself. So that is why it's called as one port. In the two port, we can have the provision of applying the signal across or actuating the transducer across one capacitive gap and sensing the signal across another capacitive gap. So for example, we take a look at here in this particular structure right here. So this structure is essentially what we already explained. So take a look at this structure. So now you have this beam over here, which is same as previous one, clamped at both the ends, and then there is a bottom electrode. One is called drive electrode, and beneath this beam there is this sense electrode. So similarly, similar to the previous case, we are applying this voltage VP to polarize this beam over here, and to one of the electrode beneath this beam we are applying the Vi of t, which is the AC input signal, which so together with Vi of t plus Vp, this beam is driven into a resonance, or this beam starts vibrating at a resonance frequency, and there is this capacitance right over here, and there is this another capacitance right over here. So output, where is the output we are taking? In the previous case we are taking the output from the beam itself. So as across this single capacitance gap we are actuating the transducer and sensing the output signal across this single capacitance gap over here. But in this situation we are driving it across one capacitive gap, and we are sensing it so across another capacitive gap, and the feed through path from input to output is like this. This is the feed through path that we can see that. Okay, and here is the current that we are sensing. This is the output signal. So this is called as two-port device, or two-port signal transduction. This is called as one-port signal transduction. So what is the advantage of this two, or difference between these two? Here we have this capacitance which is there, which is inherently there, but because of the splitting of these two electrodes, we have split the electrodes from 1 into 2. So what we can see here is that the total capacitance is now, let's say this is the C1 and this is C2. So total capacitance is 1 over C1 plus 1 over C2. So it's like if the C1 and C2 are equal, so the total capacitance is C by 2. So the capacitance is reduced. So we've seen that the total current is the admittance j omega c into Vi of t plus eta into dx dt. So that's the motional part, and if this this signal, or say this current component is higher than this current component, so it's difficult to detect the signal due to motion, and we are interested into this component. We are interested into this component over here. So attempt should be made to reduce the output current due to this component while designing. So while one port capacitance we have this CF, so this capacitance is CF, is larger in the one port combination over here. However, because of the splitting of these electrodes from 1 into 2, the effective capacitance goes down. So we have a benefit of reducing the component, output current component, due to feed through in the two port combination. So that is the advantage, and the attempt should be made to reduce the component due to the feed through. Another way, we can also reduce the omega, which is the frequency of the drive. So if these omega, which is frequency in rad per second, angular frequency, if that goes high, so the current due to feed through also dominates, and then current due to motion, it's difficult to detect this current. So that is the uh, importance of the current, and that is the explanation of the feed through capacitance in the mechanical transducer, when based which are based on the capacitance change. Alright, so now the question is how to fabricate such structure. Right over here, this is our mechanical structure. How to fabricate such structure? So let us take a look at that. So this is the fabrication uh, that we briefly tried to discuss, and from this we'll be able to see feed through capacitance, and from this we'll be able to derive an equivalent electrical circuit for this, electrical equivalent circuit for this. We see that we start with silicon substrate, which is a p-type or n-type substrate. Based on that, which is indicated by this pink color, and then this is an oxide, the orange one. This is usually SiO2, silicon dioxide, that is deposited over here. And then there is a photolithography process by which the mask is patterned, and then there is a etching, and then there is again a deposition of this metal layer. This is a metal layer which acts as a bottom electrode to drive this beam which is on that. Then again there is a etching process, photolithography, and then there is a etching on which we see that we'll have some uh, certain areas that have been etched away again. So this cycle goes on, and this top portion, that is our metal, or let's say it could be a polysilicon, or it could be a metal of which this beam uh, structure is made of. So we have this bottom electrode, now we have this beam, then there is a silicon dioxide. To the bottom electrode we are going to apply AC voltage. To the top beam, to the structure itself, we are going to apply this DC voltage to polarize it, and the output is going to be sensed from the body of the vibrating element itself. So this is basically your current over here. And where is the feed through now? The feed through is from input to output. So here is this capacitance, and the feed through path is like this over here. Okay, so the total current is going to be uh, is equal to the summation of feed through plus your current due to motion, that is Im. Okay, so now how to draw an equivalent circuit for such structure based on that. So we have to first identify the various parasitics uh, associated with this mechanical structure. So let's say this is silicon substrate, which is p-type or n-type, so it has a doping, so there is a resistance associated with it. So there is a resistance R. And then this is a metal, that's an oxide, that's a silicon at the bottom. So we have this capacitance, one capacitance over here. So we can say that there is a one capacitance over here. Then there is a another capacitance that we have seen over here. We can see that there is another capacitance. However, they are not coming into these two capacitances, and this resistance, they're not coming into the signal path. Or we can neglect this resistance because this is quite trivial over here. So these capacitances, they are not coming into the signal path from input to the output. This is an output. So the equivalent circuit we can derive. So before that we have to convert this mechanical structure into an electrical one. So for that, what we can do here, we first have understand the analogy.